Hello, good morning, everyone, and welcome to today's guest lecture. My name is Adam, and my presentation is going to be on LiveLink, where we had some sensor networks that were deployed in the forest, and we are going to share some of the experiences that we had deploying the IoT battery-free sensors in the forest. So the presentation is going to be based on this outline. So why we need battery-free, energy harvesting, wireless sensing, and then the LiveLink design, the lessons learned from the deployment. Yeah.
Could you maybe use microphone?
You cannot hear me well.
But I have some hearing.
Okay, is that okay now? Yeah, okay. So this is our outline for today's presentation. And maybe I put it here. Can you hear? Or it's gone? Okay. Yeah, so as we know, Internet of Things is the internetworking of physical devices embedded within electronics that are able to do some kind of actuation, sensing, interactions, and thereby be able to collect and exchange data over the network or over the internet. So basically, an IoT node comprises of some kind of the sensing node, the gateway or internet, and then the back end. So depending on how a particular node is designed or how it's been expected to perform its expected tasks. So, however, in IoT, we have traditionally IoT devices are powered using batteries. However, there are two twin challenges with traditional battery-powered IoT nodes. So one of the challenges is that everything in the IoT architecture or IoT node relies on the power block. That means the communication layer, the processing layer, the sensing layer, and everything is powered from this power block. So using batteries, they have some the downsides, like limited lifetime, waste when they are being used up, and then so you can see here we are trying to avoid the pollution that is being caused by the batteries, or frequent replacement in the case of the IoT node is deployed somewhere in remote places or hard to reach areas where it is difficult or is cost intensive to replace such kind of batteries when deployed. So is battery-free IoT device possible? This is a question that people used to ask. Well, depends. There are some ongoing researches that have been carried out to see the possibility of having a battery-free IoT devices. That is against the traditional battery-powered IoT architecture. So in one of the approaches, the IoT node architecture has been modified in such a way that the battery is augmented with energy harvesting module. So you have your traditional IoT node architecture, then you have energy harvesting module like a solar panel, then that is augmented just to support the use of rechargeable battery here. However, this modified architecture also still has the effect of using the actual traditional battery, because when the battery dies, then you need to go and replace the battery, which the lifetime doesn't span of more than 3.5 years at most. So still, this modified architecture do give some kind of support to the IoT node architecture, but it doesn't completely solve the issue at hand. So that is why we move to the next. So in the second approach, the IoT node architecture is modified where the battery is integrated with some kind of supercap storage, so that we have the energy harvesting module then integrated with the traditional battery, and on top of it, then there is an addition of the supercap storage. However, we still have our culprit here, that is the battery, which remains still within the architecture. So we are going to get rid of the batteries now. So in the third iteration of the IoT node architecture, we arrived at the power block where we have only the energy harvesting module, then supported by the supercaps storage, because supercaps are regarded as environmentally friendly, and their lifetime tends to be thousands of years or hundreds of years, that thousands of charge cycle. So that is why we think this architecture is the most preferred one. So, and it's regarded as the battery-free IoT node architecture. So does this solve everything regarding the IoT node or IoT system that we tend to have? Well, there are still some pain points with this modified architecture that we have just shown, the final iteration that we have. So two things: unreliable and dynamic nature of energy harvesting, because assuming you are using solar panel or to harvest the energy from the environment, the energy that you get from the environment is dynamic and is unpredictable. At least you don't know when to harvest, or there will be some kind of environmental changes that will lead to instability of the energy that you can harvest. And secondly, using supercaps brings the issue of high discharge rate and also the low energy density when you compare it with the traditional battery. So these are still the twin challenges that needs to be addressed in the battery-free and energy harvesting IoT node. So in trying to address this problem, we designed Flute, which is a platform that enables the development of battery-free and energy harvesting IoT systems. So it just is modular and compact. So the next speaker will try to elaborate more on that. So the Flute delivers a modular and compact design that can be used for portable and mobile applications. It supports also a plug and play for various IoT boards that are in the format of Adafruit feeder devices. And also it comes with intelligent charge management libraries where you can be able to manage the energy in your IoT node. And lastly, it's ultra low cost power, it's battery free, and also supports energy harvesting modules. So the takeaway, using Flute, you can be able to have a reliable, battery-free IoT development platform. So you can see the diagram of the Flute power management board that we have. So this is the charge storage. This is the management, the hardware management system, and this is where you put your development board. And then here you connect the energy harvesting module. So we are going to see in the next, in the subsequent slides. So now the question is, how reliable and efficient can battery-free wireless system be in the field? So now we have seen the modification. No, it's okay. So we have seen the modified architecture. We have seen the Flute, where it supports the building and development of battery-free and energy harvesting IoT systems or IoT nodes. Now, how is the performance of this IoT architecture in the field, or IoT nodes that we built from the Flute in the field? So we have designed LiveLink. However, just taking back to the state of the art of real-world deployment of battery-free and energy harvesting systems, actually, they are very rare to find a long term or deployed battery-free IoT nodes, but there is the most common one that has been recently published in the literature by Cycus Maximus from Italy, some researchers. They deployed battery-free and energy harvesting sensors. However, in their approach, they applied intermittent computing approach, which simply means in their own approach, they accept failures in their own deployed systems. And their findings, so they have 3 iterations of the system that they built. The first one, they call it Kingdom, which is battery baseline. That is, it has the traditional battery architecture. Then the second build node that they have deployed is called Republic, which has an energy harvesting module. And then in their own third iteration, they have Empire, which also integrates some improvement based on the experience that they have deploying Kingdom and the Republic. So in their own findings, they were able to achieve 71% availability using the traditional battery. So they ran the experiment for a period of 2 years. So the battery-based node has an uptime of 71%. Republic, which is a battery-free node architecture, yielded 22% compared to the Kingdom baseline. And then finally, the last iteration yielded about 25% of So the experiment, as I mentioned, ran for 2 years without maintenance. That is good, but then with some ups and downs. So limitation of their approach, availability far below the application needs. For instance, if we try to adapt their system in kind of other applications like flood monitoring, like wildfire monitoring and other places, then this kind of approach may not work. Why? Because they do apply intermittent computing. Intermittent computing approach accepts failures. That means nodes can fail if there is no energy or if something happens in the software. Then if the condition revives, then it will kick up from where it stopped and then continues with its tasks. However, in some applications like flood monitoring, like some forest monitoring, wildfire, you don't need such kind of approach. So that means adopting this kind of approach may not be applicable in such scenarios. So real-world energy harvesting deployment area, and they lack continuous computing approach where the node remains active and can be able to execute tasks whenever it is needed. So this is a challenge that we have identified in the literature. So with LeapLink, we have chosen an application case of forest monitoring where we deployed a couple of nodes that are built based on the Flute node architecture that has been shown earlier to support research on the forest microclimate, where we can be able to monitor the forest and then sense and then collect some data from the forest and then send it to be used by the environmental scientists in order to develop to better understand the microclimate and ecosystem dynamics. So there are 2 motivations for our application case. The first one is the issue of climate change, which demands continuous long-term environmental monitoring. And then the second one is the battery-based systems, because we are trying to move away from using the traditional batteries. And then the battery-based systems requires high maintenance, and also they have a low lifespan, limited lifespan. So, however, there are some key challenges deploying this kind of nodes in the forest environments. The first challenge is the dense or seasonal canopy that reduces the availability of the energy that you can have in the forest environments. In our case, we are using a solar energy harvesting. So you can imagine if you deploy a node, inside a densely populated forest. So how much energy you can be able to get while using the solar energy harvesting. And the second challenge, we are using supercaps that have a very low energy density compared to traditional batteries, and also they have a very low, so that means you are not risks brown out. It means you need to have an intelligent energy management if you would like to have a continuous data delivery in such scenario. So these are the challenges. So we think this is the perfect place to compare the performance of the traditional battery IoT node architecture with our own modified battery-free node architecture. So this is the LeafLink in a nutshell. It contains, it's a scalable IoT sensor network with energy harvesting and LP1 connectivity. We use LoRaWAN network to support the connectivity or the communication, the transmission of the data from the node that is deployed inside the forest to our server. And also it has intelligent charge management libraries that has been deployed that has been developed from the flute. And then it also, it's ultra low cost power. Of course, it is battery free and supports energy harvesting operation. This is a representative node that has been deployed in the forest where they are attached to the tree trunks. And this also forms the foundation for a long-term study of the battery-free energy harvesting system that is deployed in the forest. So the experiment ran for a period of 2 months where we have a side-by-side evaluation with the battery-based baseline for the same type of node. So this is the hardware architecture of the LeafLink that is built on the flute. So you can see here, this is the energy harvesting module where it harvests the energy. In our case, we use a solar panel to harvest energy, one single solar panel to harvest the energy. This is the energy management circuit where we have a voltage monitor, harvester, isolator, and so on. I think the second speaker can explain more on the architecture of the flute. And then finally, we have our sensors connected. So in the LeafLink, we use BME 680 sensor from the Bosch, where it's one of the commonly used environmental sensor in the field. And for the software architecture of the LeafLink, so we have 3 interaction modules. The first module is the energy management, where we have from the energy harvester that we have shown in the previous, and it interacts with the energy aware scheduler from the flute that has been deployed. And then we also have a sensor management module where it interacts with the scheduler. And then finally, we have our network stack that is used to communicate the sensed parameters from the node. And then we have our backend where we push our data. So feel free to stop me if you have any question. Maybe we can. Yes?
What is flute?
Flute is, I have introduced the flute before, but it's a platform that enables the development of battery-free and energy harvesting IoT node. So it has the energy harvesting hardware, and then it supports the transformation of battery-free, the traditional IoT boards into battery-free and energy harvesting. So the paper is online, and then I'm not sure if we have uploaded flute, but you can be able to see it. So now we are testing how the flute performs in the real world. So besides just the development of the flute itself, then we have to evaluate its performance in the field. So that is why LeafLink is built on top of the flute, just to evaluate the performance. Okay, so this is a side-by-side some of the key features that we have for the two nodes that we have built for the evaluation of LeafLink for the battery-free and the battery-powered nodes. So on the storage side, as earlier mentioned, we use supercaps. So we use 4 by 15 farad supercapacitors in the battery-free node. However, in the battery-based one, we use a LiPo battery, as you can see there. And also for the lifetime, this is a theoretical lifetime, of course, but yeah, this is what we have. And then for the battery-based ones, they have limited cycle life. And also, in terms of the cost, while the upfront cost here, you can see it's higher, but it's better in the long term. So you have the initial upfront cost that is higher, but then if you include the maintenance needed for the battery-based node, then that one will double the difference. And also, in terms of the energy management, we use some adaptive control switch. However, in the case of battery-based node, you always need a linear charge regulator. So if you are integrating a battery-based IoT node with an energy harvesting module, you always need a charge regulator. Otherwise, the node cannot function properly. However, in the case of this, we don't need the linear charge regulator. So, and so on. So the key takeaway from the side-by-side comparison between the two nodes, you can see the battery-free node tends to offer long lifetime based on the hardware components, including the energy storage. However, for the battery base, the needed replacement of the batteries frequently tends to offer a very low or a costly maintenance approach. And also, in terms of sustainability, yes, the supercaps are more sustainable when compared to the battery. And then the downside is you have lower energy in your system when compared to the battery-based approach. So thereby offering some limitations. So this is the architecture of how the deployment was done in the forest. So we deployed 10 nodes, 5 battery-based nodes and 5 battery-free nodes. Each node is placed on a tree trunk, as you can see here. So that is how we disperse the node across the forest. And then we have a gateway at the edge of the forest in order to help with the transmission of the data that is being collected by the nodes. Now, does LeafLink deliver expectations? So that is when we see with the evaluation. So you have seen the design, the motivations behind, and the deployment and the positioning. Now we are going to see the evaluation of the LeafLink itself. So we position the evaluation as the lessons learned from the field, because we tend to make it like an experience-based study, so that to see how it will actually behave when deployed. So lesson 1, battery-free does not mean lower reliability, because as some researchers or some engineers feel that using only battery-free system, you tend to have a very low reliability. However, in our experiences, we tend to have otherwise experience from the LeafLink. So you can see on the battery-free nodes, so 2 nodes encountered lower reliability. But what do you mean by reliability? So in this case, we have 2 categories of reliability. We have what we call a power failure. Power failure means a node has lower energy to support operations. So unavoidably, it has to fail. On the other hand, we have a software failure where you have enough energy in your tank, but due to some software failures, like the program crashes or there is a network loss, then the node cannot be able to execute an expected operation. So this is what we evaluated in the lesson 1. That is, how is reliable to use the battery-free nodes in terms of the power failure and in terms of the software failures. So we observed that 2 of the battery-free nodes encountered such kind of failures. So the battery-powered nodes also we had encountered similar kind of failures. So in the battery-free nodes, there was a downtime due to a software bug. Subsequently, in the battery-powered node, also there were some downtimes due to some brownout. However, in the battery-powered node, they were able to recover after the failure due to that is the power failure. As a result of power failure, the 2 nodes were able to recover when the energy, when the condition changes. However, with the battery-powered nodes, once they depleted, they were not able to recover. So can you guess the reasons? Can someone sense why? Why should we be able to recover when there was a power failure? However, we missed the other one in the battery-based nodes. Any idea? Okay, we will see in the future. So in terms of recovery, the battery-free nodes recover faster. However, the battery-powered nodes requires a threshold, a minimum input voltage of about 4.65 volts. Why? Because of the linear charge regulator. As we mentioned earlier, the battery-powered node always requires a charge regulator to be integrated with the energy harvesting module. So in this situation, due to the limitation of the charge regulator, it requires a minimum input voltage that may sometimes not be possible to achieve due to the reduced canopy in the forest environment. That is why all the failed nodes were not able to recover quickly. So in terms of the efficiency, it uses almost all the harvested energy. However, when tested for the battery-based nodes, so there is always a reduction, like a wasted about 2% of the input energy that is being consumed by the charging circuit. So the question now is, why do these perform better? So based on the 3 reasons. 1, the use of adaptive charge management system, and then the use of appropriately specified supercapacitors, and then lastly, because charging is possible at a very low input voltage and current in the case of battery-free nodes, whereas it's not the same in the case of battery-powered nodes. So our findings shows that the battery-free node achieve higher reliability, that is 60%, about 60% more than the battery-based nodes. However, this is in contrast with some prior studies where they were able to achieve a lower reliability when compared with the traditional battery system. So in terms of the efficiency in this science means how efficient the node is able to perform the scheduled tasks. So we evaluate the efficiency here based on the average daily messages that is being transmitted by the nodes. So the median average daily messages that has been recorded by the battery-free nodes is higher than the average daily messages that is being recorded by the battery-based nodes due to some of the failures that have been affected by the battery-based nodes as described previously. And similarly, the deviation from the topmost performance battery-free nodes with the battery, the topmost deviation between the highest performing node and the lowest performing node is higher when compared to the topmost deviation between the battery-based nodes. So here, in terms of the efficiency for successful task execution, we have seen that the battery-free nodes deliver more tasks when compared with the battery-based nodes. So in terms of the reliability of our LoRaWAN network in the forest, the nodes were equally affected by the problem. So you can see, but however, they have achieved at least 25% reliability. So the red one indicates the battery-free link reliability, and the blue lines indicate the battery-free node reliability. So they were almost equally affected by the network problems in the forest environment. So here there is no winner, there is no loser, we could say. Yeah, because it's something that is beyond the control of the node. It's something that has to do with the LoRa link connectivity. So finally, energy subsystem dimensions drive efficiency. Part of the lessons we learned is that how you design the energy storage majorly affects the performance of the nodes. So this shows a situation we call high voltage shut-off mode. Remember, apologies, I didn't show that, that slide here. So the configurations of our battery-free nodes and the battery-based nodes. So in order to prevent the supercapacitors from damage, we have what we call Vmax. We have set a maximum voltage that you can charge it to. Otherwise, then something that is needed will happen. So in essence, if after deploying the two nodes, they are charging, so the battery-free node tends to reach the max voltage higher because they can be able to support early recharging when compared to the battery-based nodes. So the battery-powered nodes, they were able to take longer time before they can fill the tank. However, the battery-free nodes, they quickly fill the tank. So in that situation, we need to disconnect the energy harvesting from the storage. So that is what we have shown here. It means this graph indicates the percentage of time that the nodes remain disconnected. There is available solar energy, but unfortunately, our supercaps is filled, so we have to disconnect it from charging. That means if you go back and review the design, you can make it a bit higher or a bit lower depending on your test. So in this situation, it means we have more abundant energy that we can be able to reuse, but however, due to the user-defined, remember it's user-defined, you can be able to raise it or you can be able, but for safety, we tried to make it at 5.4 voltage so that once it reaches this level, then all possible charging will be disconnected. So this is what we call. So it's part of the lessons we learn that the energy subsystem design drives efficiency. So that is very important whenever you are designing your battery-free IoT nodes. So in conclusion, we have had a 2 months forest deployment, a side-by-side experience study between the battery-free and battery-free nodes. And then our findings show that the battery-free nodes have fewer failures in comparison with the battery-powered nodes. And also, the battery-free nodes tends to have faster recovery due to the charging mechanism between the two systems. And then also the battery-free nodes has higher efficiency in terms of the number of tasks that is delivered daily. We have seen already previously. However, why? Because the battery powered is mostly limited by the charging inefficiencies, because the charging is blocked at at lower voltage and current input. So all the energy below the threshold of the charging circuit is being wasted. So that is very important, and also the downside of using a battery-powered IoT systems. So in our future approach, of course, if someone picks an interest here, can be able to say, okay, let's see if we can be able to extend the lip link to something else, or if we can have a better experience, or if we can be able to, like in your projects. So extend the deployment to capture some seasonal effect. Of course, we know is one of the limitations of our current study that it doesn't go throughout the year. So as we can see more variations in the, and also have more statistical analysis, and also scaling the network. Of course, someone can say, okay, I will try to deploy 20 more nodes of the battery-free nodes to see how really they can behave in the forest environment, or then deployment in another diverse environments, because these were deployed in Belgium, so someone can say, okay, let me try to deploy it far side of the Belgium or even in another place. So the key takeaway here is adaptive battery-free designs enable long-term, low maintenance, and battery-free operations. Thank you. So if you have any questions, we can. Yes.
I was thinking about since most of the projects are into the nature or outside, like the drain system or something, the river monitoring.
Yeah.
We discussed earlier.
Yeah.
Is there any kind of work happening for the using the nature as like biochemical cells or something, so that like even though if there is no sun or if there is less solar dependency, can we use the nature in any way to support our energy?
Yes, I think there are some researches that they use other form of energy harvesting mechanisms, like you mentioned, where you can. So I remember there is a research from an Antwerp group where they use a soil moisture energy harvesting, where they put the sensor and they harvest energy based on the differences in the energy gradients in the soil. I think it's something that is possible. You are not restricted only to using the solar energy harvesting, but there are many other opportunities as well. Yeah. Okay.
And what do you think about the efficiency or the consistency or the reliability of this kind of?
Yes. So actually, before you select a particular energy harvesting, it's contextual, because it depends on your application needs as well. So maybe is the environment where you are going to deploy your sensors that becomes a constraint that you have to use a particular energy harvesting source. So there is no any general rule that says, okay, you have to adopt to this kind of energy harvesting mechanism, because like right now there is one of your colleagues who is doing a wildlife tracking project for sea animals. So imagine if you say, okay, I would like to use a solar energy harvesting in the sea environment. It may or it may not be feasible, you know? So that depends on the context of where you are applying the, yeah. Yeah, but in general, if it is a terrestrial deployment, I think solar energy harvesting is the best if the application permits. Yeah. So any other question? Okay, so the next speaker will.
Good morning, everyone. First of all, I think I need to introduce a little bit about myself. My name is Van Vũ Bùi, and I come from Vietnam. I'm a PhD student under the supervision of Professor Danny, and today I'm very honored to be here to give my presentation about flood monitoring. In our world, we use battery-free IoT for monitoring flood in Vietnam. Actually, this is a project granted by Belgian government. And after we designed and developed our battery-free IoT node for monitoring flood, we will bring our work and deploy it in Vietnam to monitor flood in some rivers in Vietnam and in Belgium also. This is the outline of my presentation. First, I will give you the motivation why we should use battery-free IoT for monitoring flood. And next, I will show you the flood tracker, the IoT node for monitoring flood. Finally, the evaluation and some conclusion about the reliability of the node and the potential ability to use battery-free IoT node for monitoring flood in tropical countries and in European countries also. Everyone here knows that floods are among the most devastating natural disaster all over the world. And despite a significant effort to mitigate the impact of flood, they continue to inflict harm to people's lives, people's life, and damage to infrastructure. And good news is that IoT technology can help mitigate their flood impact. So we can deploy the IoT node in the upstream of the river, in the forest, far from the citizens. And then when a flood happens, the IoT node can send the water level from the upstream of the river or in the forest to their prevention agency. So that they can have some appropriate method to mitigate their negative impact of flood. So the question is why we need to use battery-free IoT node for monitoring flood instead of using the battery-powered IoT node. Most of IoT devices nowadays, they relied on batteries with operational lifetime of just a few years, and this can lead to some negative impact on our environment because batteries is toxic. It contains some toxic metals such as lead, lithium, and or camera is something like this. In addition to this, because the lifetime of the battery is quite short. So it means that after deployed the node in the field, for a short time, we need to replace the battery. And we can imagine that if we deployed hundreds node IoT, IoT nodes in the field, in the forest, in the upstream, and then after a certain amount of time, for example, a few months or a few years, we need to access the forest, the difficult to access area to replace the battery. It is challenging. Energy harvesting in combination with supercapacitor energy storage can help deal with the disadvantages of battery power I just mentioned above. The reason for this is that it is more environmentally friendly. it doesn't contain toxic metal like the battery. And the second reason is that the lifetime of the battery, for example, for the lifetime of the supercapacitor is very long, based on the calculation from the data sheet of the manufacturer of the supercapacitor we use on flood tracker node. The supercapacitor can offer the lifetime of around 1,000 years theoretically. I just mentioned for electricity stuff, not mentioned to the firmware. I mean that we need to update the firmware. We didn't mention that. So the question is that supercapacitor have a lot of advantages, like I just mentioned. So what is the challenges when we use the supercapacitor? The challenges is that the energy density of the supercapacitor is much lower than that of the battery. So we need to build the hardware and the software that can make the battery-free IoT node can work reliably. And one thing we need to consider when we designed a battery-free IoT node for monitoring flood is what type of sensor we should use. Traditional research, the researcher used the contact sensors. The contact sensor. This is the one of the contact sensors, the pressure sensor, to detect the water level. And this is the image. One of researcher used the pressure sensor to detect the water level. This is the node, the solar panel, and the MCU in the enclosure here. And then we need to use a metal top to connect the sensor to our node here, because the sensor here need to be deployed in the river, in the water. So we need the metal tube here to rotate the sensor. However, when serious flood happen, it can sweep the sensor. And a lot of node in flood node in Vietnam, they use the traditional contact sensors to detect the water level. And after a certain amount of time, they need to do maintenance, because when serious happen, it swept the sensor. One disadvantage of their contact sensor is that because when flood happen, there are a lot of mud in the river water. So the mud accumulation in the water can lead to some negative impact on the sensor readings. The reason for this is that the sensor, based on the pressure, affected on the sensor to calculate the water level. However, when there is a lot of mud attached to the sensor reading is not accurate. In addition to this, other aquatic organisms also have some negative effect on the sensor reading, because the sensor is deployed in the water. To deal with this problem, researchers have increasingly used the non-contact sensors, the ultrasonic sensors, to detect the water level. These non-contact sensors can help deal with the issues of the contact sensors I just mentioned above. For example, is low cost and accurate, easy to deploy, but the new issue arise here. For the ultrasonic sensor, the range is limited. For example, in Vietnam, there are some dam or bridge where we need to deploy the IoT node, the distance is very high. I mean, when a serious flood happened, the water level fluctuated significantly. If we use the sensor with the short range, we cannot detect the water level. So this is why in our world, I mean flood tracker node, we are going to we use the novel non-contact sensors, the LiDAR sensors. I will explain more later about this sensor. This is the hardware of the flood tracker. Because the hardware of the flood tracker is quite similar to the Leuven and Adam. My colleagues already present earlier, so I would dive deeply into the hardware of the flood tracker. I just present the MCU. I mean, there is a difference in the flood tracker compared to the Leuven here. For the IoT board here, we use the NRF 9160. Actually, it's a development, the feeder board that can support the NB IoT and LTE network to send data from the node to the server. Here we have the energy harvester. We use solar panel to harvest energy from the environment. We have the solar energy monitoring so that we can sense the light level here to detect whether it's night or it's daytime. And we also have the supercapacitor here to store the energy. For the converter here, because the flood tracker node integrate two types of sensor, the ultrasonic sensor and the LiDAR sensor. So we need the converter so that we can provide, the flood tracker node can provide the suitable voltage to each type of sensors. This is the image of our BC board, I mean the motor board, and this is the NF 9160 to work as the main controller of the flood tracker and send data to the server. For the solar panel, we use a very small solar panel with a dimension just 70 and 55 millimeters to harvest energy from the environment. As I mentioned before, in the flood tracker use two types of sensor. The first sensor is ultrasonic sensor, and the second one is the LiDAR sensor. For the ultrasonic sensor, we can deploy in some location where I mean, when flood happen, the water level just fluctuates, not much. And for the LiDAR sensor, we are going to deploy the flood tracker node with the LiDAR sensor when at high dam at high bridge. When we compare to type of sensors, we can see that for the ultrasonic sensor, the current consumption, the average current consumption is just around 15 milliamp. For the LiDAR sensor, the current consumption is much higher, 85 milliamp. However, the range of the LiDAR sensor is much higher than, longer than the maximum range of the ultrasonic sensor. For the ultrasonic sensor, the power supply from 3.3 to 5 volts, and for the LiDAR sensor, it should be 5 volts. And this is the image of the enclosure we designed for our flood tracker node. This is the software of flood tracker node. Actually, yeah, for the software stack, for the software stack, there is a similar between the Leuven and the flood tracker node. They use the flood algorithm to adapt the touch rate of the node. I mean, to manage the energy of the flood tracker node, and also manage the operation of the node. The core of the flood tracker software is that the flood algorithm here, it is an energy-aware adaptive algorithm that can adapt the touch rate of the node. The touch rate of the flood tracker based on the energy available in the supercapacitor and the energy we can collect from the environment. And flood tracker will send data to the server via the NB-IoT network. So the question is that why we use the NB-IoT network to send the data to the server. The reason for this is that because we can make use of the NB-IoT PSZM feeder to make our node very, very low power during its idle mode. This is just the average power consumption of the NF9160 when we use the NB-IoT PSM feature. It's just 15 microwatt. It's very, very low power. And this is this is the profile of the flood tracker node. When we try to send a package of 1,500 bytes to the server every 2 minutes, the power consumption is 21 milliwatt. However, if we send the data to the server every 2 hours, the power consumption is just 0.4 milliwatt. And this is the image of our node deployed at the dam in Vietnam. And this is the node we deployed in Leuven. Actually, for this 2 nodes, we deployed over there. Just 5 minutes working from here to the node, right? The IMAX parking. And we deployed our nodes in the field for 5 months so that we can get data and have some analysis about the reliability of flood tracker node when we deployed in the real world. This is a power consumption of our flood tracker node when it sleeps and when it is in active mode. For the ultrasonic node, when the node is in sleep mode, it consumes only 163 microamp. However, in the active mode, the mode the node sends water levels and data to the server, and the time the node need to go into the sleep mode. The average power consumption is the average current consumption is 26 milliamp, and for the LiDAR node, we can see that the average current consumption when it is in sleep mode is similar to the ultrasonic node. However, for the active mode, the average current consumption is much higher. The reason for this, as I mentioned before, because the current consumption of the LiDAR sensor is much higher than that of the ultrasonic sensor. during 5-month experiment in the real world in both Belgium and in Vietnam, we have the average touch rate of the LiDAR and ultrasonic node deployed in Vietnam and in Belgium, as you can see on the screen. Let's compare the average touch rate of the node of the LiDAR node deployed in Belgium and the ultrasonic node deployed in Belgium. We can see that the touch rate of the ultrasonic node is higher than that of the LiDAR node. The reason for this, you can see that the average touch rate of the LiDAR node is that sending a message every 9 minutes. However, for the ultrasonics, the touch rate is higher. It's then the message to the server every 6 minutes. So it means that a flight tracker can automatically adapt the touch rate to different type of sensor based on the power demands of the sensor. And when we compare the average touch rate of the LiDAR node deployed in Belgium and the LiDAR node deployed in Vietnam here, we can see that the touch rate of the node deployed in Vietnam is higher than touch rate of the LiDAR node deployed in Leuven. The reason for this is that because in Vietnam, the average light level is higher than that in Belgium. So it means that the flight tracker can adapt the touch rate based on the energy available in their environment. And this figure shows the touch rate distribution comparison across 4 nodes. I mean 2 nodes in Vietnam and 2 nodes in Belgium. Have a look at the figure. We can see that the most common sleep period here is close to the minimum value. I'm sorry, I think I need to talk a little bit about the figure. This figure shows the distribution, I mean the touch rate distribution of the 4 nodes organized in 5 minutes buckets based on the sleep in interval of each node. For the axis here, show the sleep interval range, and for the white axis here, so the percentage of message. I mean that the percentage of sleep interval fall into each bucket here. So the most sleep period is close to minimum value. I mean that the minimum value is the highest possible touch rate. It means that the flight tracker can adapt its touch rate so that it can send the data to the server as much as possible. I mean that the flight tracker can optimize the touch rate. And I have a look at the figure in more detail. From this bucket to this bucket, we can see that 93% breeding have sleep interval of 30 minutes or less. It means that the flight tracker can work reliable and it can adapt the touch rate to the minimum value. I mean that can optimize the touch rate. I mean can send the data to the server as fast as possible. This table shows the high voltage startup mode. I mean the time the node worked in the high voltage startup mode. So what is the high voltage startup mode? Actually, this is the mode the flood tracker stop observing the energy from the environment to prevent supercapacitor overvoltage, to protect our supercapacitor and protect our MCU. Based on the table here, we can see that an average of 32% and 47% in high voltage setup mode. And this shows that flood tracker can handle their power-hungry sensors, or it can support other power-hungry wireless communications, for example, satellite communication. That I think that is what Lars is doing. He's using the flood tracker, integrate satellite communication to track wild animals. I think maybe this next year we'll have other presentation relating to using the satellite communication to battery-free node, integrate the satellite communication for tracking animal. This is the supercapacitor voltage data from the LiDAR and ultrasonic sensor deployed in Vietnam. For that, I will skip this slide because the time is limited. This is a water level collected by the ultrasonic sensor and LiDAR sensor we deployed in Vietnam for 5 months. The result show that the average deviation when we compare the sensor reading of the LiDAR sensor to ultrasonic sensors is 3 centimeters. One issue we have when we try to deploy the flood tracker node in the field is that during 5-month experiment, we have a period the sensor readings is not accurate. The reason for this is that when we deployed our node in the field, and there are some dead and floating tree accumulating beneath the sensor detection zone here, and this do some negative impact on the sensor reading. To deal with this problem, our colleagues, I'm collaborating with one of colleagues in the DistriNet lab in Seoul to use the IoT node, battery-free IoT node, and a camera to run machine learning to detect the water level. And this is the evaluation sensor performance when we deployed the flood tracker node in Leuven. This is a LiDAR node, and this is the ultrasonic node, and we compare the sensor reading of our flood tracker node with the LiDAR node. The LiDAR with the radar node. This radar node is the node operated by the Belgian government. So, and we have some comparison between the accuracy of this node together. And the result show that the average deviation of the LiDAR node we compare the sensor reading to the radar sensor is just 2 centimeters here. Let's see. We have actually this is the link. We can have a look at the sensor reading of the ultrasonic sensor and LiDAR sensor and compare the result of compare the sensor readings to the sensor reading of the node from the government here. So finally, after 5 months, I deployed the battery-free IoT node for monitoring flood in the real world. We have some result I would like to show you. First, flood tracker integrated the novel long-range sensor that can support detect water level with a range 4 times longer than traditional sensor, and it is the non-contact sensors, so it can reduce the maintenance cost, and in addition to this, it can help reduce the time and effort to deploy in the real world. And flood tracker also have the intelligent power management that can help. The flood tracker can work well and reliably when we deploy it in the real world. And during our during the experiment, we also noticed that the flood tracker can achieve 100% energy availability. I mean that there is no problem with the node cooled by the energy. In addition to this, we have a high level of reliability of the node. I mean, the flood tracker node can get 98% uptime. During our experiment in the field, we have a problem is that sometimes the cellular provider, the network provider, they did the maintenance their system. So we have 1 day the node cannot send data to the server, but this not come from the power failure. This make it a compelling solution for sustainable and real-world flood monitoring. So it means that if we use the battery-free IoT node and deployed the battery-free IoT node in the field, it can meet any requirement, and we can apply battery-free IoT node in the field in the future. Thank you so much for your presentation, and if you have any question, please. I'm sorry because my presentation have a lot of analysis relating to the battery-free stuff, so maybe it. Oh, sorry.
Just like if you use solar power for powering your devices, this is a bit of an issue because it's like if it's really raining a lot, then you don't get as much sunlight when you get in the flood.
Yeah, you mean that actually the flood tracker is supported by the intelligent power management. So when we have little, I mean that when the low level, when the lower light level, the flood tracker automatically adapt the test rate based on the energy available in the supercapacitor. So during, you mean that when flood happen and the light level is low, it can have some negative impact on the flood tracker node. However, because the flood tracker node have their intelligent power management, so we can deal with this problem well. Actually, how to say that? This is the intelligent power management, so it can adapt the test rate based on the energy available in the supercapacitor. So, in case of we have very low light level, and then the flood tracker can adapt the test rate. I mean that the speed the flood trackers and data to the server is lower to make sure that the node can maintain its reliability in the field. Yeah. Do you have any question? Sorry, Adam. I think. Yeah. Okay. Maybe.
Yeah, okay, thank you. I think if no question, then we call it a day.